So I would like to talk about detectors today. And gravitational wave detectors, of course, spans quite a large field. This is a plot from a Nature paper we put out last year that spans something like 25 orders of magnitude in frequency, all the way from stuff at the Hubble scale to gigahertz scale. And it spans something like 10 orders of magnitude in amplitude. And in this plot, there's an awful lot of different ways to detect gravitational waves. I am unfortunately going to have to ignore things like CMB and Planck. I'm going to have to ignore pulsar timing array, which I hope Stan talked about during his talk, I'm told. And I'm going to focus on these things, and thematically these things, LISA, Advanced LIGO, Virgo didn't make it onto this one, share interferometry. So I'll talk about interferometry for gravitational wave detection. And Patrick asked me specifically to try and talk about what detector and network capabilities will maximize the science. And unfortunately, fortunately for me, this conference has actually been talking a lot about that. So I've been learning here about different networks and analysis. What I'd like to do is mainly just tell you the status of the experimental efforts in these places. And the one thing I want to point out is Planck released their first data, an early source catalog, kind of last week, I think, very recently. So Planck is actually making data. So it's kind of cool. LISA, we all know about. It's 3 spacecrafts flying around the sun, which is not in here, detecting gravitational waves from things like supermassive black holes. In terms of frequency range, it extends all the way down to fractions of a year up to fractions of a second. In terms of, fractions of a minute in terms of range. And a strain sensitivity down to something like 10 to the minus 24. We're all familiar with it. The idea is that you have 2 test masses in a spacecraft, and you have a laser that measures the distance, tracks the distance back and forth, and you do some sort of nifty interferometry to measure the displacement between each of your 3 spacecraft. LISA is always going to be flying. It's currently supposed to fly in 2025. The thing that's supposed to fly in the near term is LISA Pathfinder. And it's a technical demonstrator that demonstrates the required relative acceleration noise for 2 test masses. And it does so by flying 2 test masses in the same spacecraft and trying to keep the spacecraft still. To give you a sense of scale, here's 10 to the minus 10 meters per second squared per root hertz. Here is 10 to the minus 14. This is the LISA requirement out to 1 millihertz. This is 1/10 of a hertz here. This is a mission that's currently in orbit. This mission is in orbit. This mission is supposed to fly as a test of the equivalence principle. And here's LISA Pathfinder. Here's what they have to do as their mission. Here's what they think they will do. So they think they will demonstrate LISA-based acceleration noise. And the amazing thing about LISA Pathfinder is it more or less exists. Here is the spacecraft doing testing. These little things here are the magic thrusters that give it the low acceleration noise. And this thing here is the test mass that they will sense, one of the 2 test masses. It's meant to be as much of the same flight hardware in terms of microthrusters and control systems as LISA as possible. The piece that's missing, of course, is the link that goes 50 million kilometers. There was just recently a report that this is delayed a little bit. It's not clear immediately how long it's delayed, but it's supposed to launch in something like 2013. Okay. In the meantime, there is another mission on orbit that does gravity. It does, from the point of view of gravitational waves, a little bit of prosaic gravity. It measures the gravity of the Earth. This is a map of the Earth as measured by its gravitational field. And so, for instance, you can see the Andes Mountains down here. It's called the GRACE mission. It's actually the Gravity Recovery and Climate Explorer mission. And it turns out this is the way that climate scientists are measuring things like the ice cap on Greenland. And here's 4 years of the ice cap. And you can see the annual variation here in the Greenland ice cap. This is actually the big earthquake in Indonesia. And the point is this mission is ending soon. The way it works is there's 2 satellites that fly in orbit, and they measure the distance with a microwave link. So the climate community wants them to put up another mission. And the gravitational wave community is asking or has gotten permission to put a laser link in between these two satellites. And that laser link will use much of the same interferometry, at least in terms of what the laser looks like and how you measure the distance between these two satellites, as LISA Pathfinder. It's meant to launch in 2015. To give you a sense there, here is the, again, this is unfortunately in different units. This is displacement in meters per root hertz. Here's what GRACE sees now. This is kind of the signal from the Earth. Here is what the interferometer link will do. And here is what LISA's link will do. So, in terms of absolute scale, not so much, but in terms of flying a LISA space hardware, certainly I am very, very excited about this prospect, and so are some of our colleagues. Pretty firm launch in 2015. Which brings me to something a little more grounded. Thank you. This is the current and future ground network of gravitational wave interferometers. I work on LIGO, which is these two sites, two interferometers in the Hanford, Washington site, one interferometer in the Louisiana site. They're both 4 kilometers long, or at least will be for advanced LIGO. There is the GEO 600 site outside of Hanover. That's a 600-meter interferometer. And the Virgo, advanced Virgo site outside of Pisa. A new experiment is LCGT that's a little bit cut off on this screen, but this is an underground interferometer that just received approval in Japan in the Kamioka mine. And we're pushing, we would very much like to see LIGO Australia, which would be a 4-kilometer long interferometer outside of Gingin in Australia. So that's the network as it stands. Just based on yesterday's discussion, I wanted to do a quick review of what we mean by range. Specifically, this here is the antenna pattern of a Michelson interferometer to gravitational waves. This is the response to the two polarizations, the cross and plus polarization. If you try and evaluate the signal-to-noise ratio of an inspiraling chirp, it's a function of position on the sky. This is two sky coordinates and 2 orbital coordinates. It's a function of the chirp mass here. So this is the term theta that leads this equation. This is the signal to noise. This is the antenna pattern here. Z is Z. This is the chirp mass and the distance. And then here is the noise in our detector. So this is how we evaluate what we expect our inspiral range to be. If you take a detector network, of course, and you spread them around the Earth, you get different coverage on the sky. This is actually kind of regions of constant signal to noise. This doesn't actually tell you how deep the signal to noise goes, but of course that varies with the network as well. This is for a Hanford, Livingston, and Pisa network. And then there's another piece here, which is it depends on whether we're talking about the horizon distance or the range. And the horizon distance is the farthest point we can see for an optimally oriented signal. The range is if you took this volume and you treated it as a sphere. That's what the range is. So that's kind of where this factor of 2 is floating around that we're always talking about, and that there might be some confusion of. And yeah, it comes into the source inclination in this term, okay? So that's where a lot of this factor of 2 comes from. We, of course, argue about it amongst ourselves, too. So in this talk, will be using horizon, okay? So in terms of schedule for the next few years, we're sitting here nicely in 2011. In the, say, last 5 years, we've had the LIGO, Enhanced LIGO, and Advanced LIGO projects. I'll talk a little bit about that. Virgo has gone through their first detector, the first generation detector, cleverly named Virgo. They're an upgrade called Virgo Plus, which is underway now, and Advanced Virgo, which is coming up soon. GEO was one of the first detectors to get close to their sensitivity and is now pushing their high frequency sensitivity in a program called GEO-HF. LCGT, as I said, was funded earlier this year and is in its design and construction phase. They should get to some kind of interferometry in, say, 2014, and hopefully be online with the rest of us in 2017 or 18. And then LIGO Australia, as a project, would begin construction sometime in 2012. And join us. Yes?
Quick question. For LCGT, is the initial sensitivity comparable to advanced LIGO?
Their target sensitivity is comparable to advanced LIGO. Yes, absolutely. Absolutely. They get there in a slightly different way, but they're
The target.
their target. I mean, the goal of LIGO, Virgo, LCGT, and of course LIGO Australia is to, or LIGO Gold, is to be, all have the comparable sensitivity and to all be online in 2018.
LCGT is actually slightly more efficient and slightly more sensitive.
I don't think it's more sensitive. I have a slide at the end that compares design curves. It's shorter. So its displacement sensitivity is better, but its overall strain sensitivity is not.
I thought its inspire range would be slightly better.
But I only have the power spectra. I haven't actually calculated it. So the enhanced generation of detectors, or the plus generation of detectors, kind of ran in this period from, say, 2008 to now. From enhanced LIGO, we did a series of improvements that were targeting something like a factor of 2 improvement in range. In particular, we wanted to roll out as much advanced LIGO technology as possible, so that goes from such things as new readout techniques to increasing the laser power and rolling out some advanced LIGO data acquisition systems. Virgo Plus increases the laser power and changes the optics of their arm cavity to higher finesse, and that those two things together push the sort of best sensitivity to a lower frequency. And then they changed their suspension to monolithic suspension. That means that their test mass is held by all glass fibers, and that is for thermal noise reasons. So that should really open up the low frequency end of their performance. GeoHF is going in exactly the opposite direction because they're 600 meters. They are a little bit shorter. So they're increasing the laser power and aiming for high frequency performance. So they'd like to do better up at a kilohertz. In particular, they're doing some nice quantum measurements using squeezed light. So this is how enhanced LIGO did. We ran for a while with Virgo in its original configuration, and then Virgo Plus joined us again in August for the end of our run. It was a little bit rockier than initial LIGO, if you remember the initial LIGO spectrum. But in terms of neutron star horizon range, we went from something like 30 to a little bit over, almost 45, almost 50 for a few days in there. But something like a little bit over 40 megaparsecs by the end of our run. Altogether, single interferometer, so this ran for about a little over a year on the calendar. In terms of coverage, we had one interferometer on for about 11 months, a little bit less than 11 months. And we had 2 interferometers on for something like 5 or 6 months, coincident. And just to give you a sense, this is a histogram of all the different science mode segments. You can see, kind of a bimodal distribution that mainly has to do with the fact that we did a lot of commissioning in this break here and really improved the sensitivity. So Virgo Plus, as I said, they're intending to run through this summer. Increased laser power, I already said this. This is actually what the suspension looks like. This is the beautiful optic here, one piece of the optic. And here you can maybe barely see it is fused silica fibers. And the intent there is to lower the thermal noise, which comes in here in the spectrum. And of course, the scary part is that you've now taken your most favorite mirror and hung it from pieces of glass. And Virgo really led the way on this in the modern generation, developing this system. And they have very good performance from their suspensions, very high quality factors. This is the Virgo sensitivity here in blue with the design in red. The Virgo Plus design curve is in black here, and as you can see, opens up all of this low frequency range. Just to give you a sense, this curve corresponds to something like 25 megaparsecs, and this curve corresponds to something like 100 megaparsecs neutron star horizon distance. GeoHF is a kind of remarkable experiment. I have to say, this is the Geo corner station here. There's where the beam splitter is, and in here are the other mirrors. This is the squeezer. This is what it takes to do the squeezed light quantum measurement that they've done. They've done it all with a very small group. And they've already demonstrated squeezing on this interferometer. That's a paper that's due out soon, so I won't say any more. But I will say this is what their target sensitivities are. Here is how they did in September. It's in light gray. I'm sorry if you can't see it in the back. But here's the curve here. And this green curve is what you expect from shot noise. So they're basically right on top of shot noise. They're right on top of a quantum limit from a kilohertz all the way up. When they add squeezed light, they intend to get to this cyan curve here. This is 6 dB of squeezing. And the point of squeezing is that it buys you, in the case of 6 dB of squeezing, it buys you a factor of 2 in your shot noise sensitivity without turning up your laser power. If you had to turn up your laser power, you'd have to turn your laser power up by a factor of 4. And that starts to get painful. After that, once they demonstrate the squeezing, they go and shift their optics and go for a high frequency tune. So at the end of the day, they are aiming for this black curve here. And of course, they intend to do that in the near term so that they will be online during the dark period of advanced LIGO and advanced Virgo. To give you a sense of scale, there's the LIGO Virgo kind of shot noise sensitivity.
Are they going to get the low frequencies down too?
They hope to, but that's not actually, their focus is in here. So one of the nice things about the high frequency program is they're not trying to do the low frequency part.
I just was wondering because you see the curve up there.
Yeah, no, the curve extends up there, and that's been, you know, that's of course been a major source of work. They're returning to night and weekend mode now, so they commission during the day and run over the weekends. As I said, LCGT is funded. It's a project led by ICRR at the University of Tokyo. Here is the kind of expectation. This here, I don't know if you are familiar with, is the Super K experiment. This is a cavern underneath the, I can't pronounce this, but it's in the Kamioka mine. Camland is next door to it. It's an interesting place because you just drive sideways into the mountain, and once you've driven in for a few kilometers, you find yourself under a giant pile of rock, which is great for low background neutrino experiments. It also turns out to be a seismically pretty good place for gravitational wave experiment. So their plan is to build into the mountain a 3-kilometer long interferometer, and that's shown here. They already have in the mountain a 100-meter long interferometer that's in, it's actually right, there it is right there. No, right there. It's a 100-meter long interferometer, and it's cryogenic. So the way that CLEO and the Large Cryogenic Gravitational Wave Telescope goes after thermal noise, in part is the monolithic suspension, but the other part is to turn down the temperature. Okay, so that's how they get their low frequency performance. This is what they expect to do. To give you, this is their 300-meter prototype that is working in Tokyo. This is the shot noise curve here, and I'm sorry, I did not calculate the inspiral range, but I thought that this ends up being a little bit less than the best advanced LIGO range. You can see here, here's the suspension thermal noise. It's the dominant radiation pressure noise. Photons actually pushing their mirrors around is the dominant noise source, but that's because turning the temperature down brings the thermal noise out of band. Okay. So advanced LIGO, you've seen these a lot. It's just basically, you should focus on this, a beam splitter, and these two guys, end mirrors. It's a Michelson interferometer. Compared to initial LIGO, we turn the power up so that we go from up to 750 kilowatts of stored light in these arms. That's a lot. We improve the isolation. So this has gone from a simple pendulum to a quadruple pendulum. And it's gone from a passive stack to an active stack. So this now has something like 6 stages of active isolation. We do these funny zigzag shapes in here. The reason we do that is to make these recycling cavities longer so that we can make them stable. That was one of our big problems in the first generation of interferometers. We add this signal recycling mirror that allows us to tune the sensitivity like GEO does. And we change the readout scale. And mainly we change the readout so that we can go to this high power and to avoid some technical noises. Probably the most important fact about advanced LIGO, at least for me anyway, is that it began now last year in October of 2010. So we turned off the interferometers and you know, basically some guy immediately pulled one of the vacuum chamber doors off to make sure that advanced LIGO was really starting. You can't go back anymore. And in fact, the LIGO interferometers are basically empty at this point. They're removing the large optics now. So the Livingston interferometers. This is how we intend to do. This is the initial LIGO noise curve from S6. This is the advanced LIGO design curve in the neutron star optimum tuning. You can see in the best 100 hertz band here, we do something better than 1/10 of an attometer. Seismic isolation is low frequency. The suspension thermal noise is this mid band, and the laser power is this high band. So from a schedule perspective, We took our detector handoff. We're doing a single arm test, so we're trying to run one of these magic quadruple pendulums in a 4-kilometer long cavity this summer. And then next fall, we're building up the Livingston Vertex and the H1 squeezer. Kind of an important point is the next fall we will also be making a decision on whether or not we go with LIGO Australia. So after that, the next milestone, spring of 2012, so something over a year from now, we expect to have all of the pieces in the vacuum system in the Livingston interferometer. Basically, a year after that, the first Hanford interferometer, and a year after that, the second Hanford interferometer. So we should have all interferometers built in 2014, and that's probably the earliest you can imagine taking a science run. And just to give a sense, this is my own personal speculation. This is not collaboration approved design. But my guess is we're going to turn on with something like this green curve here. And I bet we're going to turn on with this green curve really pretty quickly. We're going to see that in 2015, 2014. And what this curve is we're running at low powers. So our shot noise limit isn't really very good. And we have some excess noise down here at low frequencies that we haven't figured out yet. We haven't explored that region of space yet. We don't have the sensitivity with advanced LIGO. But this curve here already, this green curve, is already 130 megaparsecs for a neutron star horizon. It's already 4 times better than initial LIGO was. And for black holes, this is 3030 black holes here. If they exist, we can see that out to 270 megaparsecs. And each one of these kind of steps represents, say, 6 months of commissioning work. We figure out some of the low frequency, so we go to 8 watts and low frequency, and that really gets us sensitivity to black hole signals. Then we go to, we add a signal recycling mirror, and that gets us sort of into this region here. And then our design curve has got a neutron star horizon distance of 460 megaparsecs. Okay, just based on a rates paper in CQG that Ilya put together with a lot of help from other folks, that's something like 40 neutron stars per year and 20 black holes per year for this best curve. Okay, there's this link. You can go to it. It's public. I encourage you to use these 2 curves because we're not going to do any of the rest of these to start with until we find sources that really make it worth it to go for these other tunings. It's pretty progress. We're on target. We're two and a half years in and change, and we're 40% complete. For installation and on budget, I mean, there's just a lot of things to do to make one of these complicated systems. So, Advanced Virgo looks schematically very much the same. The difference is their isolation system is this giant tower. They are also underway. Their procurement has started. They have some design decisions that are yet to be finalized, of course, so don't we all. Their installation is to begin in July of 2011, and their goal is to return to operation coincident with Advanced LIGO in 2015. So finally, LIGO Australia. This is something that, of course, people in this room are very interested in. Here's the detector network with the 2 US sites and the Virgo site. Here's the detector network as you add Australia. And you can see you've gone from something like 10 square degrees for a high SNR source to something like 1. The idea here is that Australia provides all the buildings and people, and we provide an interferometer with no new cost or delay to Advanced LIGO. Advanced LIGO is the #1 thing, so you don't get to hold that. It's been approved by the National Science Foundation and is currently in the Australian funding agency's lap. It could be online by 2017 if it gets approved. So the future is very bright. LISA technology could be on orbit in 2013, and with the GRACE mission, we can be doing satellite-to-satellite interferometry in 2015. The Virgo, the 2 European interferometers, Virgo Plus and GeoHF, are online and commissioning and making rapid strides. Advanced LIGO is 40% complete, and we're on schedule at this time. Earliest science run conceivable, I think, in that low power configuration in 2014. So that's certainly what I'm looking forward to. And it just, it's pretty amazing. We could have 6 detectors around the world online in 2018. So that's really what I think we all should push for, because that's going to be a good good, bright future. So thank you all very much.
Hi, I have two questions. The first one, the location, the orientation of the arms in Australia, is it free or do they have some geographical constraint to have them in a certain way? The second question is that, are the GEO folks interested in the squeezing or they don't plan to have it?
Buried in the schedule for advanced LIGO is a Hanford test of squeezing. So we're putting a squeezer on the output of the H1 interferometer actually now. The goal is starting in September, we're going to do a 4-month commissioning run with it. If we can show low frequency squeezing, so squeezing down at the 100 hertz bucket, and that works and doesn't introduce awful amounts of noise and things like that, my guess is that every interferometer will have squeezing. It's just too good. It's like manna from heaven. There are things going forward with squeezing about whether or not you do explicitly a quantum non-demolition design where you try and have output filter cavities and stuff. Nobody's got that in their baseline right now. The first question about the Jinjin orientation is, I believe it is constrained, but Stan knows the answer to this much better than I do.
Yeah, it is constrained, and we have actually made a decision about the orientation, and it's optimized relative to the other networks, the other detectors.
So it has been decided, but the geography doesn't constrain.
The geography does. There's a road. So we're rotated about 17 degrees from a north-south, east-west direction in the counterclockwise direction, and that bumps up against the road.
Okay, so we have time for one more question.
Sure. Oh, well. Don't be too polite here, we'll run out of time.
In the GRACE interferometer, is there any hope of doing science with that, or is that just purely a testing ground for technology?
Wow. What a loaded question that is.
The Earth scientists think they're doing science.
And so did the instrument scientists. I mean, just as a, just to throw out a bone there. Are you going to do, GR relevant geodesy with it? No. It's made to measure the motion of, it's made to measure little g.
I think the question is, could they replace the microwave link with that?
They absolutely could replace the microwave link with the laser link. They're not willing to. So the way to think of this is you can't fly anything in space that hasn't been proven to fly into space. So if you can hijack, if you can hitch a ride on someone else's mission and get flight-proven hardware on a mission that's already going, that has the climate group pushing for it, you go ahead and thumb a ride. The hope is that not only will it test the data, but the hope is that the data will be of such superior quality that that's what they will use. But, so.
Okay, let's
Thank you.
Sandra.
You mean